Well, exam 2 is in the books, and so it's time to march onward. We pivot. Again, we have made the pivot. We have moved away from derivatives and moved toward these other things that are eventually going to solve an area problem. And to do that, we want to talk about the definite integral. A couple of lessons ago, we talked about the indefinite integral. This is a definite integral. And here's the box from Strang's book. If f of x is a function defined on some interval, the definite integral of f from a to b is given by, this is the integral symbol, the integral from a to b of f of x dx. We say the dx, even though the dx is just part of the notation. It has meaning. It came from somewhere. We'll talk about where it came from as time goes on. This is the integral symbol. It's an elongated S, and it goes at the beginning of the notation. So if we write the integral symbol from a to b of f of x dx, it's the same a and the same b. This definite integral is this thing that we talked about in a previous lesson. So this part right here is the sum of areas of n rectangles. And these were the rectangles that we made up where the height of each rectangle is given by some function value. Any function value on the interval is fine. And this is the width of every rectangle. These are the little delta x's as we go. So if we take the sum of the areas of n rectangles, heights and widths, we sum them up, there are n of them, and then we take that limit as n goes to infinity. In other words, we have more and more rectangles, they get thinner and thinner and thinner. And if we have more and more rectangles and they get thinner and thinner and thinner, and that process goes somewhere, we say that this limit is the definite integral from a to b of f of x dx. What kinds of functions are integrable? All continuous functions are integrable. So all of the functions we're going to take integrals of are continuous. Easy that way. As a quick side note, that variable is what we call a dummy variable. It's called a dummy variable, meaning that there's no special meaning behind the x. If we were to write the integral from a to b of f of x dx, and we were to write the integral from a to b of f of t dt, and we were to write the integral from a to b of f of chicken nuggets d chicken nugget, none of that all of these are the same. None of that matters. The differences between x and t and nuggets are irrelevant. It doesn't matter. What matters is the function and the interval on which we're working. So the actual variable itself is irrelevant. We can swap that out as long as we swap it out in both places, swap it out in both places, swap it out in both places. Okay, so let's apply the definition. Let's take a look at x squared on 0 to 2. Let's take a look at x squared on 0 to 2. Let us find the integral from 0 to 2 of x squared dx, which means what we're really looking for is this area in here. So how do we do that? Well, we split the interval up into a bunch of rectangles. How many subintervals do we use? We use n subintervals. Well, if this has length 2, and we break it up into n pieces, each of the little pieces is 2 over n. So delta x is this difference divided by n. That's the delta x. So what about the heights? Well, the heights depend on these x values. So what we do here is we pick a specific one along the way. We pick the ith endpoint. Well, if the first one's at 2 over n, and the second one is at 4 over n, and the third one is at 6 over n, and the fourth one is at 8 over n, the ith one is at 2I over n. That's the ith right endpoint. So we're going to set up our sum. I'm going to take the sum, as I goes from 1 to n, of f of x sub I star times delta x. That's a sum, as I goes from 1 to n, of f of our special place, f of this. So how do you find f of this? Well, you take that and you stick it into the function. Times delta x, that's delta x. And then a lot of what happens next is algebra, or if you prefer, magic. 2 squared is 4 times 2 more is 8. I squared is I squared. N squared times n is n cubed. So the question is, what is that? What is that? Well, 8's a regular American number. And n cubed is a regular American number. Remember, n is just the number of subintervals that we used. So n's a number. It's fixed. And because these are fixed numbers, we can pull them right out. We can't pull the i's out because the i's are changing. Right? The i's are changing. We're adding up I squared, 1 squared, 2 squared, 3 squared, and so on. The i's are changing, but the n is not changing. N is always what it was. So I guess the real question is, what is this? And for that, well, I have to give you some formulas. So there are 3 formulas that people generally keep track of. The sum of the i's, and the sum of the I squareds, and the sum of the I cubes. And these are things that we kind of keep handy. We don't memorize them. We do not memorize them, although I did, and that's probably my own fault. It is not necessary to memorize these things. So in this case, we lean on this formula and we make that substitution. So this is 8 over n cubed times n plus 1, 2n plus 1 over 6. So what does that mean? We should pause for a moment and see what that means. What does that mean? That means that if we break this interval into n subintervals, this will be the area that we find. So if we break this up into 4 subintervals, 4, 4, 4, 4, that's the area. It's an approximation, but that's the area. If we break this up into 2,000 some odd subintervals, 2,000 some odd, 2,000 some odd, 2,000 some odd, 2,000 some odd, whatever that is, that's the approximate area that we get by using 2,000 some odd subintervals. What are we interested in? We are interested in the integral from 0 to 2 of f of x dx, which means we want the limit as n approaches infinity of this thing. Well, what is this thing? Well, a little bit of algebra tells us that this is 16n cubed plus 24n squared plus n over 6n cubed. And we learned that when the highest powers were the same in numerator and denominator, these didn't really matter. They go to 0 effectively. And what we're left with is 16 sixths. That's 8 thirds. So the integral from 0 to 2 of x squared dx is 8/3, meaning that this area is 8/3. Exactly. It's not an approximation. Exactly. I will demonstrate one more time. Find the integral from 0 to 3 of 3x plus 2 dx. So how does this go? You got some function from 0 to 3. We're going to break it up into a bunch of rectangles, break it up into a bunch of subintervals. There's the ith one there, and then there's some at the end. How many subintervals are there? There are n subintervals, which means that delta x is end minus beginning over n. That's 3 over n. So this is 3 over n, that's 6 over n, that's 9 over n. The ith one is 3I over n, because that's the first, that's the second, that's the third, that's the ith. So what do we set up? We set up the sum as I goes from 1 to n of f of x sub I star delta x. Well, what is that? F of x sub I star, that's f of this number. So we take that and we put it in here and we get 3 of those plus 2 times delta x. Then we do a little bit of algebra. It's nothing terribly complicated. We're just going to distribute this guy all the way through. So that's 27I over n squared plus 6 over n. And because that's a sum, we can break this sucker up into the sum of 27I over n squared and the sum of 6 over n. So how do we evaluate these? Well, 27 over n squared is a number that's going to come out. And then what's left is the sum of the i's. And the sum of the i's is this thing. And then 6 over n, well, that's not bad. And then what we're left with is the sum of 1. We're left with the sum of 1. So now I got to ask you, you add up 1, 1 plus 1 plus 1 plus 1 plus 1 plus 1 until there are n of them. Right? If I add up 5 ones, I get 5. If I add up 10 ones, I get 10. If I add up 2,000 some odd ones, I get 2,000 some odd. So the sum of ones is n. So what do we got here? We've got 27n squared plus 27n over 2n squared plus 6. Well, what happens now? The integral from 0 to 3 of 3x plus 2 is the limit as n approaches infinity of this thing. Well, what's that? Well, as n goes to infinity, these go to 27 halves, and 6 is 6. So that's 39 halves. Problem solved. 39 halves. Okay? Okay. There's going to be another video. It's going to talk about areas without having to do this process because it doesn't need to be done all the time. And then we'll show up in class and talk about all of it.